Bueno, gente, gracias por venir este día viernes. Hoy día les quiero presentar a la profesora Macarena Lagos, estudiante de licenciatura y magíster de esta misma casa de estudios, estudiante doctoral en la Universidad de postdoc de la Universidad de Chicago, la Universidad de Columbia, y actualmente profesora de la Universidad de Maryland, que nos va a presentar The Multi-Messenger Proofs of Parity Symmetry. Así que bueno, un fuerte aplauso, por favor.
Hola a todos, gracias por la invitación. Prefiero hacer la charla en inglés si están todos ok con eso. Ya. Entonces, I'm going to talk about using cosmological observations from gravitational waves and electromagnetic counterparts to prove fundamental symmetries about the universe, focusing particularly on parity symmetry. So let me just start with a brief introduction on what parity symmetry means. And we say we have parity symmetry when our observables are invariant under point reflection. And let me give you a very specific example here. So we have this tetrahedron, and if you make a point reflection from, let's say, this right image, you obtain the left one, and you can convince yourself that you can never get the left image just by making rotations, for example, 3D rotations from the right image. So this is certainly a distinct type of symmetry from the ones that we're used to, like rotations. So these type of kind of figures do have cosmological applications. For example, if you search for 4-point correlation functions of any scalar observable, then you can search this type of configurations, 4-point configurations, and search for parity symmetry. Another example that is important in physics and cosmology is in the case of the helicity or the spin of particles. So when we have parity transformations, we basically change the helicity of particles from, for example, left-handed, right-handed, or vice versa. So this is the idea that we're going to have in mind. And we know that in nature, parity symmetry is not fully preserved, and at least in the weak force, it's known to be broken. And now the question is, how about gravity, or specifically cosmology? So we know that general relativity, at least, is a parity symmetric theory. But cosmology, of course, is much more complicated because you have to add matter fields. And these matter fields could have parity breaking interactions with gravity. And especially, we have a lot of unknown components in cosmology, such as the inflationary field, dark matter, dark energy, all these components that we don't know exactly how they interact. And the idea that we could have cosmological fields that break parity, dates back from like the 60s or 70s in the case of inflation. But more lately, this idea of searching for parity violation in cosmology has been regaining attention because of two recent claims in which they analyze actual data from the cosmic microwave background and from the galaxy distribution of large scale structures. And these initial works from 2020 and 2022 claimed to find evidence of parity violation in these data sets. However, there has been a lot of debate on whether this was real or due to systematic effects, and they didn't account correctly for in the analysis. So there have been some later studies on saying that basically this is not necessarily correct and it has to be reanalyzed. But continuing with this idea, we are the objective of this work is to search for new type of observables to see if there is parity violation in cosmology. So in this case, we're going to use gravitational waves, and we have already actual data from gravitational waves and search if there's any evidence for parity violation in that case. So similarly to this case of the helicity of particles, in the case of gravitational waves, the way in which parity violation would show up is through its polarization. So gravitational waves, like photons, have left-handed and right-handed polarizations. And if there is parity violation, these two polarizations will behave differently. So this is the main idea that we're going to be after. So in this case, in the case of gravitational waves, they contain a lot of information, both from the strong field regime and from cosmology as well. So the emission process of these signals comes from typically black holes or very compact stars, and the emission is determined by the strong field gravity physics. But then these waves propagate for billions of years through this cosmological background. And in this propagation, they are sensitive to cosmology. And in this talk, I'm going to focus on the possibility of having parity violation during the propagation. So this is what I'm going to call cosmological parity violation. So from now on, I'm going to assume that if there is any new physics, it doesn't happen at the moment of emission, but only during propagation. So let me just start reviewing how gravitational waves propagate in the standard cosmological model the CDM based on general relativity. So this is the very basic equation that tells you how gravitational waves, which is our field HP here, propagate on a perfectly homogeneous anisotropic universe. So this is based on linear perturbation theory in general relativity. So eta here is the cosmological time, h is the Hubble rate, the expansion rate of the universe, c the speed of light, and k the wave number. So here I'm assuming that I have a Fourier expansion or a monochromatic wave. And what you can see here is that we have a very simple type of equation that looks like a damped harmonic oscillator. This is really how these waves propagate. So they propagate at the speed of light, and the energy is damped because of the expansion of the universe. And here, as you can see, my gravitational wave field has a subscript P for the polarization because they carry two polarizations, what I'm going to call the left-handed and right-handed. And in general relativity, they propagate equally. They satisfy the same equation. And this is a consequence of parity symmetry in GR. So more phenomenologically, this means that any relative amount of polarization in the left or right-handed that is being emitted by any gravitational wave source, we should detect the same type of polarization. So any polarization emitted is the same one as the detected one. It doesn't change. So basically, by predicting what is the emitted polarization, I can make a prediction of what I should detect if parity is conserved, and I can check whether that's the case or not, and whether parity violation is conserved or violated. So let me give you a review on what determines the polarization emission of gravitational wave sources. So up to now, all of the sources that we have detected so far come from binary system of black holes or neutron stars. So that's what we're going to have in mind. And we're going to characterize the polarization of our signal by the ratio of how much left-handed or right-handed amount in the signal I have. So this ratio, in this case, I write it as a complex quantity. So there is an amplitude of these signals and a phase difference as well. And when we have a binary system, really the main quantity that is important is what is the plane in which the binary motion is happening. So here I have, let's say, two black holes. This system is, at least up to now, in all the detections, this plane is not precessing. It's a very simple binary, so everything, the entire motion happens in a fixed plane with a given angular momentum vector. And what determines the polarization emitted by the source depends on the exact direction in which this is emitted. Of course, it is emitted in all the directions, but in practice, I am an observer at a given location. So let me draw like an imaginary sphere, and I am the observer located somewhere along this direction. So if I can fully characterize the difference between these two vectors, this is the line of sight, and the angular momentum vector, I can fully characterize the emitted polarization. So I basically need two angles. It's just like spherical coordinates. One is this inclination angle, iota, and basically tells me how inclined this binary plane is with respect to the line of sight. And then there is this additional rotational symmetry, like even for a fixed iota, you can rotate this L like this around the line of the vertical line of sight, and that is this orientation angle psi. So what we actually know from calculating the emission of gravitational waves with general relativity is that the amplitude of this ratio of polarization fully depends on the inclination iota. It's fully determined by that, and we call that the ellipticity of the wave. Like, it basically determines whether it have a circular polarization. For example, if A is equal to 0, this would be fully right-handed signal, or if A is equal, I guess, to infinity, it would be fully left-handed. Any other combination can give you linear or some elliptical. And this phase of polarization is fully determined by this orientation angle psi. And, well, it determines the orientation of this polarization. So if you tell me the polarization, it has an elliptical shape, you need to specify like where exactly this ellipsis is pointing to. So these two quantities fully fix the relative amount of left-handed, right-handed polarizations. So I am giving you all of this information because in general relativity, what determines the emitted polarization, basically the iota and sign, is what I should detect. And I make exact predictions of what I should be detecting. Okay, so now let's make predictions of what could change if I did have some parity violating gravity, let's say an additional field that had non-minimal interactions with gravity and they violate parity. So generically, I'm going to start here with the same propagation equation as before in black, but I'm going to add these two generic modifications that I call epsilon A and epsilon V. And I want to check if now this equation, including the modifications, preserves parity or not. So when I make a parity transformation here in this equation, I have to exchange the left and right-handed polarization. So remember that P is a subscript, so really we have two separate equations, so we exchange the two equations, and because parity is a point reflection, we have to change the sign of any dependence on the wave number. So without telling you about specific theories, there's some called like Chern-Simons or different kind of modified gravity theories that are known in the literature to violate parity. What we recently did is to kind of try to characterize generically the form of these modifications in any parity violating theory. And you may already guess that if these modifications depend on the wave number k with odd powers, when I make a parity transformation, these epsilons are going to flip change. So the equation for left-handed and right-handed waves is going to look different. In particular, I'm going to have two equations with two different modifications for left-handed, right-handed, and the difference is an overall sign. If these modifications had even powers of k, then it would be some kind of modified gravity but parity preserving theory. So based on these generic modifications, I can write a solution for what I should detect in these models. And I should detect the same as in GR times some dependence on these epsilons that here I call deltas. And what you see here is that the solution for right-handed and left-handed waves is different up to this overall sign because of this thing that I mentioned here. And just to give you the result more explicitly, these delta A's and delta V modifications depend on epsilon A and epsilon V in this way. And basically, these are integrals over time. These are integrated effects because this is a cosmological effect. So it usually depends on the entire cosmological propagation time from emission to detection. So, sorry. So if, let's say, my source had no propagation time, like let's say it's like located right here, these deltas would be 0, there's no modification. But as the source is further and further away and propagates for longer times, these modifications are usually going to grow with this cosmological time. So this is just to highlight the fact that to probe this kind of modified cosmological behavior, it's better to have astrophysical sources that are pretty far away. So are there any questions up to now? No? Okay. So let me come back to this ratio. So this is really the quantity that I want to quantify, how much of each polarization there is. So based on the previous solution that I wrote, I'm gonna get that the observed ratio in this parity violating model is the same one that I should expect in GR times this correction. So this delta A has a specific name, which is called amplitude by effringence because it changes the relative amplitude of polarizations. Here I'm writing explicitly as a real exponential so that it's evident that this changes only the amplitude. And this delta V here this is a phase, and this is called velocity by effringence because really the phase of the wave is what determines the speed, the propagation speed. So this is why it has this name. And historically, as you can see here in the citation, amplitude by effringence has been studied for a couple of decades because it's a very common prediction to a lot of parity breaking modified gravity theories like Chern-Simons. But velocity by effringence is not very well explored. And what I'm going to show you next is that at least velocity by effringence can only be tested with multi-messenger sources. It's not enough to use only the gravitational wave data because there's a missing information. So the idea is that we want to observationally find a way to probe whether these delta A and delta V quantities are zero or not. So for actually probing that, I need to make assumptions. So before I said that these deltas depend on epsilon that have odd powers of k, but I need to specify exactly which powers so that I make this assumption and then I actually compare that model to the data. So here we're making a specific assumption that in which delta A and delta V basically depend on a constant parameter, kappa A and kappa B, and these parameters are the ones that I want to constrain by the data. If they are zero, there's no parity violation. If they are not zero, there is. But we also have to fix the frequency dependence, meaning how many powers of k appear in these epsilons. And here, what I assumed, basically based on effective field theory, is you assume the lowest powers possible in your model. So if we assume that epsilons, these modifications in the equation of motion, have a leading order, a linear power in k, then by looking at the delta A and delta V solutions, you obtain that delta A is proportional to k, and delta V does not have any k dependence. So this is what I assume here, and this is the reason why here there's an F, and here there's no frequency dependence on my signal. But the other thing is that these epsilons would also depend on the cosmological time. For example, if you think that what's violating parity is, I don't know, some dark energy field, then maybe it only violates parity when dark energy is dominant in the universe, like in the late time universe and not earlier. So there could be a time dependence. And in this case, we assume this specific time dependence, basically with the redshift of the source. This is the called moving distance, and this is just log of the redshift. So for longer propagation times, we have higher redshifts, and usually that will mean higher values of delta A and delta B. So these are what I said before, effects that accumulate over propagation time and are bigger for sources that are further away. So the fact that delta A is frequency dependent is very important, and it will always be frequency dependent, right? Like even here, if I assumed a different power of k, but some odd power, delta A always will have the same frequency dependence as epsilon A. So it will always be frequency dependent. In this effective field theory approach, we assume only the lowest power, which is linear enough. And this is very important because gravitational wave sources are not like a point source that you just detect like that in a given time, but you detect a time window in which the frequency of the signal can vary by 1 or 2 orders of magnitude. So we actually can see this frequency dependence in the detected signals, and here's an example. So what I'm showing you here is what is called the gravitational wave strain. So this is really what gravitational wave detectors give us as an output. It's like the exact way in which the interferometer responds to a signal, a gravitational wave signal, as a function of time for a typical binary black hole merging. So it has this typical, wiggle behavior. I guess most of you have seen upload like this, hopefully before. And in blue, you see what I would expect in general relativity, the vanilla prediction. And it always has this property in which what you can see here is that the frequency of the signal is higher here compared to here, like you see the separation here of the wiggles. So this is a case in which you can kind of bar more or less like 1 order of magnitude of frequency. And when now you introduce amplitude by effringence, and now you ask, what would I detect? You would detect here the black line, where you can indeed see that, for example, the amplitude does not change a lot here, but here, where the frequency is higher, there is like a noticeable by eye change. So this is what I was saying, that the change in amplitude by effringence, it depends on frequency, and you can see it explicitly here, and it's higher for higher frequencies. So what this means is that I cannot mimic this amplitude by effringence effect by changing, let's say, my inclination angle parameter, which is what the only way in which I could change the amplitude of the amplitude ratio of the two polarizations in general relativity is by changing this angle. But that would be a frequency independent change in the ratio, which is changing an overall angle. So basically, these amplitude by effringence modifications are unique and are distortions of the signal that I cannot mimic any other way. And basically, I could just go ahead with any gravitational wave signature and signal and ask whether I see this distortion or not. So in this case, you don't need multi-messenger signals. You can use any binary black hole that has emitted gravitational waves. And for example, this recent work used nearly 70 gravitational wave signals detected from binary black holes, search for these distortions in each one of them, and then they do what's called stacking and put them all together to get the most precise constraint, which is this one, that this Ka, they can constrain to this precision. So it cannot be a some order 1 effect, but it can be like some order 10 to the minus 2 effect. So this type of parity violation signature can be tested with any kind of gravitational wave signature. But that is not the case for velocity by effringence. In the case of velocity by effringence, because it is frequency independent, I can mimic it by simply changing the orientation angle. So any signal that has suffered from velocity by effringence, I would just interpret as a regular parity symmetric signal, but with a biased value of this orientation angle psi. So basically, the true value of that determines the actual orientation and physical properties of this binary system that I call here the emitted side is different to what I would seem to detect because it has suffered from this extra bi-effringent effect. So the question is, how do you break this degeneracy? And for that, of course, you need 2 pieces of information, right? To constrain this, you need to know this and that. So gravitational wave detections give you this. So I can just detect my signal and extract what I think the orientation angle is, the side detected. But how do I know if that was the true orientation of my binary system or not? So that I can do it with electromagnetic counterparts. So the main idea is that electromagnetic signals that now will come from binary neutron stars, not binary black holes, allow me to reconstruct what is the orientation and direction of this polarization plane and obtain this emitted or the true value of psi, the true orientation of the plane. So probably you're not familiar with like this whole electromagnetic emissions of binary neutron stars. So let me give you a review. So neutron stars are very compact objects, and they're not black holes, so things escape from them. When they merge, there is a bunch of particles, charged particles, and material being ejected at the moment of the merger. So this is what you see here, like different colors is different type of radiation. But the general idea is that we know that they detect different kind of emissions. For example, one is known as the kilonova, which is like this, I guess, blue circle is more or less some isotropic emission that is typically detected in the optical frequency band. Then you can also have a gamma ray burst, which is this jet, like in orange that you can see here. And this is basically, there is an electromagnetic field around this final remnant object, and charged particles are ejected through the poles at very high speeds, relativistic speeds, and that generates a high energy emission that looks like gamma rays. And that same jet, after a while, it starts losing energy and emits what is called the gamma ray burst afterglow, which is usually detected at lower frequencies, like even radio. Like from gamma ray, there is a continuous decay of energy until radio. So far to date, there is only one gravitational wave event from which we have confirmed associated electromagnetic emissions, which is called GW170817. So this is gravitational wave and the date that was detected in 2017, in which we detected these three types of emissions, like electromagnetic signals in the entire spectrum were detected and confirmed from this source. So why was it useful? So first, it helps you locate in the sky where this source is, because gravitational wave detectors are not like a telescope, like you don't point them in a way. They're just sitting there and they don't localize sources, basically. They detect signals from any place in the sky. So they're pretty bad at localizing sources. So you can, with the electromagnetic emission, you do have very precise sky localization, which in turn allows you to find the kind of the radial distance to the source, how far it is, the redshift. And both of these quantities are very useful to know because, of course, this also determines what I should be detecting in the gravitational wave signal. And therefore, having that information helps you break certain parameter degeneracies in the analysis. But more importantly, for polarization, this jet emission allows you to reconstruct exactly the binary properties, like where was this binary plane, these two angles of iota and psi. So here's a more detailed diagram on how the electromagnetic emission allows you to reconstruct these two angles, iota and psi. So remember that iota and psi are these angles that characterize the direction of my line of sight, so the direction to the source, with the vector that is the angular momentum vector, right? So, well, as you may already guess, the direction of the jet goes along the angular momentum vector. So the direction of the jet is determined by the entire binary momentum before the merger. So that's the main quantity contribute to the angular momentum at the end after the merger. So the whole final remnant and all of the matter around this object will be rotating with an angular vector along the binary, the original binary angular momentum vector. So if we can trace the direction of this jet, then we can reconstruct J and obtain iota psi. So in this diagram, I'm showing you what happens if I observe the emission from the jet at different times. And what's going to happen is that I'm going to see a displacement of the electromagnetic emission, like I'm going to see it coming from slightly different places in the sky. And that's going to allow me to reconstruct this direction J. So the idea is that I can make an initial emission, like at the time of the merger, T0, and that's going to give me my baseline for what is the line of sight, where the source was located. But then this jet really is a shock wave. So there's like a sharp change in the medium, and that it starts propagating. And from that front wave is really where all of the electromagnetic signals are being emitted. This shock wave, the idea is that it starts interacting with the entire medium around the source, the interstellar medium, and radiate excite electrons and radiate emission. So as I start making measurements of this electromagnetic radiation, really I'm going to be tracing the motion of the front wave or the shock wave. So if I measure at some time T1, I may see the signal coming from here because that's the location where the shock wave is. And at T2, I may see it from here and so on. And this electromagnetic emission, as I already said, initially is going to look like high energy radiation, like in the gamma rays. But then it's going to start losing energy and it's going to look like radio. And I could actually trace the motion of this shock wave for weeks or years in this radio band. So I can make like a path in the sky. So this is what this is showing you, like how I can reconstruct a path in the sky following this direction of the shock wave. So this is a different point of view, but showing the same thing. I am the observer. I make some measurement at some initial time, and I define that as my line of sight because it's the position of the source. And that's now suppose that my angular vector is pointing in some direction, J, in that along that line. And then as the shock wave moves, I'm gonna see here moving really the radiation moving like in this direction in the sky. So I can trace that displacement and reconstruct exactly where this jet is moving. So that displacement is what you see here. This is actual observational data from this GW170817 event, where you see like two angles to describe this figure in this car, declination and right ascension in milli arc seconds. And basically you measure what is the position of the electromagnetic emission at 8 days, 75 days, and so on after the merger. So I already told you, you can follow up these electromagnetic emissions for weeks or even years if you want. And what we see here really is not the actual absolute value of these locations, but the offset. So really this is defined like 0 for some arbitrary reason, but basically what this is determining the direction of the jet. So here what we do is basically we feed like a line to trace the trajectory of my shock wave and basically the angular momentum vector and obtain an angle for the true orientation angle of the binary system. And well, what you can get from here, for example, is that the precision of this measurement is of like 0.1 radian. And that is pretty good, I would say, for gravitational wave signals, because I already said they're like very bad at localizing sources and measuring angles. So having any angular measurement at 0.1 radian precision is pretty good. And in this case, this black dot was actually detected in the optical band. And then these 3 were detected in the radio band. So you can also from this jet, for example, by seeing how fast this displacement is happening as a function of time, you can also reconstruct the other angle. So you can also a little bit more precise, 0.03 radians precision. And just to give you an idea, this number in radians is like 15 degrees. So this source is basically like the plane is pretty face on, like towards us, towards the line of sight. It's very aligned, only just aligned by 15 degrees. So this is how these type of emissions can help you fully constrain these 2 angles, ion and psi, and therefore make a prediction for what the polarization of my signal should be in general relativity. So now let's use these electromagnetic measurements to constrain parity violation. First, let me tell you about amplitude birefringence. I already told you that we don't need the electromagnetic observations to constrain amplitude birefringence, but we can still use it to improve our measurements. So in the case of GW170817, this is the result. The idea that you see is like the probability distribution that we obtain for the value of kappa A. And there's a bunch of lines here, but let me show you the black dashed one, which is the result that I obtain only using gravitational wave data. And then if I start incorporating information like sky localization, distance, inclination, and so on, I can improve somewhat this measurement. And if I include all of the electromagnetic information, I get this dashed cyan line, which is, what we see is 2 effects. One is that it did make my probability distribution a little bit narrower. So that means that I can measure a little bit more precise. This parameter, the precision that at the end I obtain is this, the kappa A has to be smaller than 0.73. The other thing that we can see is that it can also help you kind of break parameter degeneracies, and that causes a shift. So it can actually help you pinpoint better exactly what is the most probable value for this object. But in any case, the previous result that I told you using 70 binary black holes, I don't know if you remember, but it was about 10 times better than the one that we obtained for 170817. And this is only because of the distance. So this source, it was very nearby, I guess for astrophysical standards. It was at 40 megaparsec, but binary black holes are measured at like gigaparsec even, like 1 gigaparsec distances. So only because of that, these binary black holes have had more time, more propagation time to accumulate bigger effects of amplitude birefringence and are better to constrain in general this effect. And this is why we decided to also make a forecast on if we detected this 170817, but now in the future, how much better could we do? And here you have 3 different configurations of my gravitational wave detectors. So 2G means like using 5 gravitational wave detectors. Then CE, for example, means, the black is that I add 1, what's called cosmic expert detector, which is similar to the one that we have now, but about 10 times better. It's a plan detector for the 2030s. And in blue, you see why we had 2 of these 10 times better gravitational wave detectors. And overall, what you see, like if you compare, here we have like order 1 constraints on kappa A, and here we have, much better constraints. So what we find is that if we detected this event in the future, when we have more and better detectors, this constraint on kappa A would improve by like 2 orders of magnitude. So that's what we expect from binary neutron stars. How about for velocity birefringence? So here is where it's really important to include the electromagnetic emission. So I already told you that this part of the information will come from the gravitational wave data, and the emitted one, or the true value of psi, will come from the electromagnetic data. So in the case of GW170817, I already told you this. This is the value that I showed you before, tracing the jet. So we have this. So how about this one? What is the detected orientation angle? And unfortunately, gravitational waves are, I already said it, are very bad at measuring angles. In this case, it was so bad that it can be anything. So like in this case, the angle goes from like 0 to pi, and this is the probability distribution that we have. And the gravitational wave data alone gives you this black line that, okay, it has a few peaks, but they're not really like sharp or meaningful. And if you include some information from the sky, but not on the jet, but on the sky localization, on distance, to help break some parameter degeneracies, you get something like clearly flat. So it can be anything. And the main reason is that the only way to measure kind of angles with gravitational wave detectors is if we have multiple of them with different orientations. Like the gravitational wave detectors are usually like formed by two arms. So they live in a given plane. So they can only detect oscillations of the spacetime or gravitational waves along that plane. But to measure polarization, you need to measure oscillations in different directions. And that's why you usually need more detectors with different locations in Earth and different orientations. So currently, there is more than one gravitational wave detector, some in the US and another one in Europe. And in principle, if they all detect any gravitational wave signal, that's enough to measure angles. But Virgo, the one in Europe, is not as sensitive as the one in the US, and sometimes it doesn't detect anything. So unfortunately for this event, Virgo did not detect anything, so we didn't have any data. So because this can be anything, even though we know the true emitted side, this could still be nothing, right? So we don't get any meaningful constraints on velocity by fringes. So again, we say, okay, what if we did detect it in the future and we did have multiple gravitational wave detectors? So this is what the gravitational wave detectors would constrain for psi. Now if we had multiple ones, I already said, for example, this Cosmic Explorer one, that is going to be much more sensitive. So if we detected again this event, 170817, we would get this black line, which is, well, now we have 3 peaks that are more meaningful than here. And we also know other type of binary systems. For example, I already said GW170817 was very phase on with 15 degrees inclination. And for measuring this displacement, it's usually good to be more inclined because you can more easily see it moving, for example. And also for the gravitational wave detectors, it's also better to have more inclination. So you get, for this one, that the main difference with 170817 is that it's more inclined. You can find, much better constraint just because of that. So if you quantify this, for example, in the red case, the best case scenario that we simulated, the gravitational wave observation alone could give you a precision on psi of 0.04 radians. So now this starts being competitive with what we were expecting from the electromagnetic data, that here we estimate at about 0.1 radian. And so this means that I can basically measure this delta V to this precision, like 0.1 radians, or well, 0.2 in this case. So if I measure delta V to 0.2, then I can translate that into a constraint of kappa V of 5 radians in this case. But so the main conclusion is that, unfortunately, because we need multi-messenger events to measure this signature of parity violation, so far there's no constraint on this effect. But hopefully in the future we will have the first constraint of this parity violating signature with the next multi-messenger event. Hopefully that will come soon. And as theories, I guess here there's a lot of theories. We can translate any constraint on this kappa A and kappa B onto specific modified gravity theories that have parity violating interactions. And at least indeed, in our paper, we did discuss a couple of modified gravity theories if you're interested. So let me just summarize the main points. So if there is parity breaking in gravity or cosmology, that's going to induce birefringent effects in the polarization of gravitational waves, in the amplitude and the phase. This type of parity violating techniques to test parity violation, really what is probing is late time cosmological parity breaking, right? Because these are sources that are very close to us, so they're only telling me if between redshift 1 and now there is any parity violation. So this is different to other studies that have used cosmic microwave background or large scale structures. This is like a complementary way because it's probing different cosmological epochs. In the case of amplitude birefringence, we can already find constraints with current detections. And I showed you that if we use binary neutron stars, we can constrain this amplitude birefringent parameter to some order 1, but that could improve by 2 orders of magnitude in the future, in the next decade. But binary black holes in general are much better just because of their higher distances. But velocity birefringence has a specific feature that is frequency independent and can only be probed with multi-messenger events. So of course, there's no binary black hole constraint so far. And the only multi-messenger event that we have, unfortunately, was not good enough to give us a constraint because we were lacking a gravitational wave network of detectors. So it does require a lot of work testing this feature of parity violation because you need a lot of gravitational wave detectors. You need to make electromagnetic follow-ups for weeks or a year after the emission. So there is a lot of work, but hopefully in the future we will get at some point the first one with this type of precision of fire radiance. So I'm going to leave it here and I'm happy to answer any questions.
Any questions?
I have a slight question, but is it possible to identify some parity violation effects with some time arrays?
So that's hard. So these propagating parity violation effects, you wouldn't see them in any stochastic background of gravitational waves.
They're erased.
Right, it's erased because they have, they have a flat distribution on this orientation angle. And even if all of these sources that are at different redshifts suffered from birefringence, then the birefringent population would still be like isotropically in this angle side. So you need individual sources with like predictions of the emitted polarization to check this.
Any other question?
I have a question. The differential equation you show in the start of this talk, if the gravitational frame is changed, this differential equation are changed, by the way?
Do you mean this one?
Yes.
Yeah, so the idea is that you change, you have some modified gravity model, and because of that, you have these new terms, because in GR you wouldn't have them. I don't know if that was the question. You would also have additional modifications that I did not add here, which is that if your modified gravity model has additional spin to fields, like multiple tensors. So there you would have this field HP, but then coupled to another field.
Are scalar, no?
So, I mean, here it's being reduced to a scalar function, but this is really a tensor, kind of like a spin to field perturbation. So if I have an additional scalar field in my model, like in most modified gravity models, this is the most general modification for the equation that you're gonna get. There's no other change that you could have.
But I think that perhaps the question was about that this equation is coordinate dependent, right? You are using as a table coordinate in order to get that one.
And sorry, what do you mean by it's coordinate dependent in that it depends on K?
To another
Right.
coordinate or another.
Well, I mean, the only assumption that I'm making here is that I have a specific background, which is my FRW metric in conformal times, but there's no other freedom. Because, so that fixes the global kind of coordinates. If I make any additional kind of infinitesimal change in the coordinates, which is the only thing that I'm allowed to do if I already fix my background, this doesn't change because the tensor perturbations don't change under this infinitesimal coordinate. So yeah, I mean, the only thing that I fixed is the cosmological background, that it has this typical conformal temporal coordinate. I don't know what that means. Okay.
Question about this parameter epsilon.
Yes.
So if you expect that one mode has a positive value and the other one a negative value,
Yes.
and you let them run for a very, very long time, you expect one node to be constant or zero, and the other one like probabilities, because you're going to cancel somehow.
Yeah, you mean like here, for example, if I wait for very long times, this delta A, let's say, grows for like an infinitely far source, and this is gonna be very suppressed, and this is gonna be
Yes.
exponentially enhanced. Yes, so in principle, that could be true, but if you formulate your theory well, it should happen, you like nothing should diverge, because here, I kind of implicitly assume that this delta A grows monotonically with distance. And usually if you're looking at nearby sources, that's the case, like if you use Chern-Simons theory, you can find that that's a true prediction. But as you go to further and further redshifts, it gets like really some kind of polynomial function of redshift, and nothing should diverge. Because all of this is linear perturbation theory, so I cannot even allow like one of these fields to grow exponentially to an arbitrarily large number. So only like in my kind of Taylor series of like linear perturbation, it's true that one is suppressed, the other one is enhanced. Yeah, that's the main effect of amplitude bifranges.
Maybe not zero, but very little number at the point that could not be detected, for instance.
Yes, I mean, there was actually one paper that used that idea to try to search for parity violation with binary black holes. So trying to find, for example, that they were all left-handed polarized, or they were all right-handed polarized, something like that, with the entire population of black holes. Yes, but as I said, like because we're working like really perturbatively, this delta A, we cannot technically allow it to be arbitrarily large. Like if this doesn't, this is the same value delta A. So if you make this very small, I mean, like this exponent very small, is because you need a very large delta A, which also makes that one grow, which is not something valued in these kind of perturbative techniques. And theories don't actually predict that.
Okay, thanks. So if there's no questions, so let's thank you. We will have a coffee break outside, so let's open to something. Primera pregunta, siguiente. Ya. Súper. Entonces, ¿quién es el primero?